right. I hope you can hear me well. Thanks a lot to the Mathematical Council of the Americas for this honor. I'm really happy to be here and have the opportunity to spend some time with you talking about math that I do like. So the topic of today is going to be surfaces in 4 dimensions. But they're not just going to be any smooth surfaces. They're going to be surfaces in 4 dimensions which have certain geometric properties, and the technical name is Lagrangian surfaces. Okay? So in order to start thinking about Lagrangian surfaces, I want to start by thinking about smooth functions and their graphs. So the graph of a smooth function f, well, suppose you have a smooth function in one variable with variable x. You can take the graph and then you can plot z equals f of x. That's the classical graph of a smooth function in one variable. You had a curve in the plane. You could do the same with a function in 2 variables. So if I have x1 and x2 variables, f of x1, x2, I can plot the graph and I get a surfaces in 3D. In the same way that the graph of a smooth function records its values, its differential records its partial derivative, specifically the first partial derivative. So for instance, if you take a function f of x and you derive it, there's a unique partial derivative that's just f prime of x, as we tell our calculus students, and the graph will look something like that. Notice that you learn some amount about f by looking at the graph of d of f. So for instance, the maximum over there will go down and exactly correspond to the 0 of the derivative. And again, I see a 0 of the derivative over here, and indeed, there's a critical point, a minimum over there. So, we tell people, and it is true, that knowing f prime of x tells you some information about f of x. Now, if instead of a 1-variable function, you have a 2-variable function, now you have 2 partial derivatives, partial x1 and partial x2, and the graph of d of f is now a surface in 4 dimensions. Because now I have x1 and x2, and now I want y1 and y2, and cut out the surface given by the equation y1 is partial x1, and y2 is partial x2. So when you're thinking about functions in 2 variables and d of f, the derivative of such functions, that defines a surface in 4 dimensions. Are we happy with this? So this is a kind of surface in 4 dimensions, and what I'll be talking about, Lagrangian surfaces, are generalizations of these specific kind of surfaces. Okay? So this is a cartoonish picture. This is a surface in 4D. Okay? I cannot draw there. All right. So let's try to think geometrically in the sense that suppose I gave you the surface to start with, but I didn't tell you who f was or df was. I just told you it is of the form df, but I'm not telling you who f is. How can you geometrically recover f up to a constant or df from the surface itself? Well, ambiently, I have coordinates x1, x2, y1, y2. And what you can do is look at the formula for d of f. d of f is first partial derivative dx1 plus second partial derivative dx2. So what you could do is you could consider the following one form, lambda standard, which is y1 dx1 plus y2 dx2. This is a one form in 4 dimensions. It is defined intrinsically. It's called the Liouville form. It has some intrinsic coordinates-free definition. But for the purposes of the talk, that's exactly how it looks like. And it has the property that when I take that one form and I restrict it to a surface of the form df, I exactly recover d of f. Why? Because y1 becomes partial x1, y2 becomes partial x2, and that's exactly d of f. And that's what I boxed for you in that equation. That equation in the box says when I restrict the one form to such a surface, I recover d of f, and therefore f up to a constant. Are we OK with that? So that's a way to geometrically use a one form to recover the f from my surface. All right. Definition that generalizes that, well, let's just say that an embedded surface L inside of R4 is said to be an exact Lagrangian if, when I restrict lambda to this L, it does have a primitive, which is to say lambda restricted to my surface L is of the form df for some f. Are we OK with that? Are we comfortable with the fact that the box in the definition is a generalization of the box before? Now, L does not have to be of the form d of f, but it will have a primitive on f. Does that make sense? All right, so let's run some examples of what things that can happen and things that cannot happen. So first of all, the examples I just gave you, if you have a function and you take the graph of d of f, is an example of an exact Lagrangian because box 1 is the same as box 2 in that case. All right? OK, here comes the fun. The fun is this kind of pictures. So nowhere in the definition is being asked that your surface is graphical with respect to x1 and x2. And that's why I try to indicate with this kind of wobbly picture over here, not saying that this is the graph of anything. Globally, it can become a non-graphical thing. And I don't know if you've dealt with this yourselves, but in math life, non-graphical things do appear, and a fair amount. And it would be wonderful for us to have a machinery to deal with non-graphical things. And in a way, symplectic topology does provide a part of such machinery. So first of all, it can be non-graphical. And the second, nowhere in there I said that L had to be a plane. It could have genus. It could be an interesting higher genus surface. And that's what I tried to depict by this first picture with the hole in there. So at first sight, when I look at these three pictures, what I'm trying to convey is L might have topology, have some genus over there. L might be non-graphical. And sometimes you can kind of pretend that it's of the form d of f, even if it isn't, because what is this? Well, this is what we would call a delta function, right? It's sort of the graph of a delta function is 0 everywhere and everything in here. So that is d of f, where f is a Heaviside step function with a discontinuity. So Lagrangian surfaces, for instance, allow you to talk about the derivative of a Heaviside function, thinking of a delta distribution, in a very graphical geometric way. So that's another example of a non-graphical exact Lagrangian that works perfectly fine. Does that make sense? All right, so what does this condition in the box, lambda restricted to L has a primitive, mean geometrically? Well, let's start with the topology. What kind of conditions do I have topologically? If you think in terms of the RAM cohomology, this is saying when I take a curve inside of my surface L, take it to be a non-trivial curve in homology, such as this one, when I integrate this one form, that has to be 0. Because otherwise, I would have a non-trivial class in H1, and then by the RAM, this wouldn't have a primitive. So it's already an integral condition that appears about integrals, certain integrals being 0. Is this like super surprising specific of surfaces? Well, not really. Think for a second about, does this thing have a primitive? Well, there's the fundamental theorem of calculus. You can integrate a one-variable function. But suppose that you wanted the primitive to be compactly supported. So suppose that you wanted an f such that when you integrate these, you end up at 0. Then you get that the integral of this business, this curve, should be 0. So you get an area condition that the top area should be the same as the bottom area. So exact Lagrangians in 1D look like curves that have the same top area and bottom area. And that's what I wrote here, area condition in 1D, if you have some boundary condition. And otherwise, the topology of L, if it has genus, spices it up with additional equations, integral equations of this form. All right? So I hope that this sets up at least what we're talking about. We're talking about surfaces in 4 dimensions, R4, and they satisfy this property that when lambda, this one form restricted to them, it's exactly of the form df, and they generalize graphs of df, being non-graphical, having topology, so on and so forth. Now, even if you don't care about any of these, which is fine, you could just start graphical, say, why should I care about non-graphical? A lot of times when you run an evolution in a physical system, a curve that started graphical becomes non-graphical. Think of a wave that starts to form and does something like that. You want to be able to still do geometry after the non-graphicality has happened. And symplectic topology, the study of surfaces, Lagrangian surfaces like that, allows you to do that. Okay? Qualitative properties of things that maybe initially were graphical, but down the road in the evolution are no longer graphical anymore. All right? OK, so let me say a couple of things. I personally enjoy the geometry of these little beasts by themselves. I think they're sort of self-worth when it comes to studying them. But their study actually connects historically to many classical things, and even more recently to other things. Maybe I'll mention something about dynamics. So when Poincaré was studying the stability of the solar system, he cared about the existence of periodic orbits. So I have a point. Will my dynamical system be such that that point goes back to itself? And then he translated that into some interesting fixed point theory and tried to state some theorems about it. Now, 100 years later, the way we in symplectic topology deal with periodic orbits, show that periodic orbits exist, is in great part by building exact Lagrangian surfaces. So I know it doesn't sound dynamical, but a way in symplectic topology to argue that a certain level set of a Hamiltonian system has a periodic orbit is you say, I'm going to take the A infinity Fukaya category of the sublevel set, show that if I have an exact Lagrangian in it, then the Hochschild chains are non-zero. And because Hochschild chain equals symplectic homology, which is generated by periodic orbits, is non-zero, therefore I have a periodic orbit. And of course, if Poincaré was here, probably he would be like, can you say that again? Because there's a lot of machinery, which is kind of more recent. But it does connect, and it is useful for things that were more classical. So if any of these words speak to you, you're absolutely welcome after my talk to come and say, well, you mentioned Morse theory or Hormander's fourth book. What is this about? And I can tell you more about it. OK, so last etymological comment here is Lagrangians were named after a mathematician called Joseph Louis Lagrange, Italian-French mathematician. And in 1788, he wrote, in my opinion, pretty dramatically, the following. So this is in the preface of his book, Mécanique Analytique, in which he established how to mathematically model kind of what now we know Lagrangian and Hamiltonian mechanics. So that was classical mechanics. Literally, you have a ball, and you throw it and try to understand where it falls. I'm going to read it for you. It says, no diagrams will be found in this work. The methods that I explain require neither geometrical nor mechanical constructions or reasoning, but only algebraic operations in accordance to regular and uniform procedure back then. All right, so this was true for his book. As you go through his book, he's true to his words, and this is indeed an accurate preface. This is no longer true in 2025. So this is a random page of one of my papers. I think that paper has about 106 pictures. So there's definitely a lot of pictures involved these days. This middle piece of work is of Salvador Dali. So Salvador Dali drew this beautiful artwork, and he called it the swallowtail, inspired by the catastrophe theory, the singularity theory developed by René Thom, and that then nowadays connects to symplectic topology. And the last one, maybe it's not a Dali, it's my kitchen. This is literally the wall of my kitchen in a Sunday morning. And it's just a beautiful caustic pattern projected onto the wall. And if you know a bit of symplectic topology, that is literally the projection of a Lagrangian in a four-dimensional space down to the wall. And it's very visible. And so I would say Lagrange might have been accurate back in the day, but today, I would say, whenever you describe a paper in symplectic, it's just the opposite of what he said. Diagrams will be found on this work, and the methods that we explained require geometrical and mechanical constructions and reasoning, and not just algebra. So we've come a long way. It's like 200-something years. I don't know how much this is in dog years, but it's a while. And it's something I really like about our field. It connects to a lot of things, and it requires different ways of thinking. All right, so now I'm going to go into the nitty-gritty of the math and what we're trying to do here, OK? So the goal, which I'm not going to achieve, is to completely classify these Lagrangian surfaces. I would like to say, here's the classification of all the possible Lagrangian surfaces. We're done. Let's go to the sessions. But we can get quite close to that. So question, what is the classification of exact Lagrangians in R4? And here, the first thing you need to be precise about is when do you consider them to be equal? And here I'm just going to tell you. You say two exact Lagrangians are considered to be equal if you have a family starting at one and ending at the other that is the identity near the boundary. So a compactly supported deformations through exact Lagrangians. All right? So if I start with this surface in here and I move it a little bit in here, I'm going to consider this deformation to be exactly the same. That's what we will call an exact Lagrangian isotopy. If you know the word, that is equivalent to a Hamiltonian isotopy. So I want to classify Lagrangians in R4 up to Hamiltonian isotopy. Now, if I had nothing to say, well, I probably wouldn't have posed the question to begin with. So one of the recent developments and things I want to tell you about is now we actually have a number of results classifying those. And we, for the first time, those results allow me to state a classification conjecture. So at least I'll be able to say, this is a conjecture of how they're classified, which is now it would be entirely an algebraic problem. So I'm not saying the algebra problem is not hard. It's in itself beautiful. But now you have removed the geometry from the picture, and you can think in different terms. All right, so let's start to be very precise about this business. First of all, we take the picture. This 4-ball, this is the picture of a 4-ball in yellow. The 2-sphere on the boundary is a 3-sphere. So really, what I drew is a 3-ball with an S2 at the boundary, a 2-sphere at the boundary. But really, it's a 4-ball with an S3 at the boundary. So the first thing you do is you fix a boundary condition. So you take this lambda over here, and now we fixed a boundary condition in here. That is typically done by specifying a link in 3-sphere, the unknot, the trefoil, your favorite link. And we're going to ask it to be a Legendrian, which for now we're just going to think of it as a good boundary condition for a Lagrangian. And then you could start to think about what happens when I change the boundary conditions, and specifically, what if I have a really simple boundary condition, like no boundary condition whatsoever? I just want closed Lagrangians. How about a closed 2-sphere inside of R4, which is Lagrangian? How about a 2-torus inside of R4, which is exact Lagrangian? Misha Gromov in 1985 proved that those cannot exist. So the boundary condition necessarily must be non-empty. Any exact Lagrangian must go to the boundary, and so the problem of classifying starts with put a boundary condition, and now try to classify those Lagrangians that have that boundary condition at infinity, or if you wish, at the 3-sphere with large enough radius. Is that clear? So that's why we have this boundary condition. So now the classification, well, if you thought about classification problems in life, they come in a lot of flavors and shapes and forms. Now, the kind of study that I want to convey here is really emphasized by that word globally. Because if you think about Riemannian geometry, there's a lot of beautiful local geometry. Sectional curvatures, Ricci curvatures, computation of local invariants. Now, the symplectic world, as it happens, has a number of results called Darboux theorems that say that there are no local invariants. Namely, 2 symplectic manifolds are going to look exactly the same locally. 2 Lagrangians are going to look exactly the same locally. So it is not possible to now take a point around this Lagrangian and come up with some incredible invariant that tells you, no, this Lagrangian is different from that one because locally they don't look the same. No, they're going to look exactly the same. So that makes the problem have a very global flavor. Again, in the spirit of knot theory, in the spirit of surfaces in 4D, smooth surfaces in 4D, it's a very global kind of phenomena. And there are no local invariants. So that's the first thing I wanted to emphasize. Now, given the boundary condition, it might be that there is a Lagrangian or not. Let's assume there is, and that makes the problem interesting, and we can classify. Otherwise, you're done with the classification. The first phenomena in contact and symplectic topology that I want to tell you about is something that you don't see in Riemannian, you don't see in smooth topology, which is we have the slight, quote-unquote, slogan that the boundary sees something about the interior. Think about a knot in S3, like the unknot. It bounds a disk, and it also bounds a once-punctured torus. And you can add as much genus as you want smoothly as a surface inside of the 4-ball. That does not happen. That's not allowed for exact Lagrangians. There's a result that says the genus of any exact Lagrangian bounding lambda is known by the boundary. Specifically, it is minimizing the genus in the 4-ball. So if I have a trefoil as my boundary condition, only a genus 1, a once-punctured torus, can be an exact Lagrangian. I'm not going to have anything like a genus 2 surface bounding it. So the boundary sees something about interior. It doesn't see it all, but it sees something about it. That makes it very different from smooth topology. Being global makes it very different from Riemannian geometry. Being known the inside from the outside makes it very different from smooth topology. The second thing is how do Lagrangians kind of talk to each other? And that's something that really makes symplectic topology sort of far apart from smooth world, which is Lagrangians behave with a very specific geometric property, and I wrote the slogan, they insist on intersecting. I'll elaborate on that a little bit, but the idea is the following. Say you have a function, a continuous function on a compact space. What do we teach our students? A continuous function on a compact space has a minimum and it has a maximum. Okay? Think in terms of a smooth function. A smooth function, having a minimum and a maximum, say in a closed space, means its differential vanishes in at least 2 points. The one for the minimum and the one for the maximum if it's not a constant function. In general, functions have critical points constrained by the shape of the space. For instance, if you have any space, any smooth manifold, and you have a smooth function with exactly 2 critical points, then necessarily that manifold needs to be homeomorphic to a sphere. So it's not possible, for instance, in the 2 torus or the 3 torus to find a function with just 2 critical points. You must have critical points accounting for kind of the topology in the middle. For instance, it's a fun exercise. Any smooth function on a torus must have at least three critical points, and generically will have at least 4 critical points. If it's Morse, it will have 4 critical points. So you see more intersections than they are required smoothly. And it comes from generalizing this 0 intersected with the f. Those are the Morse inequalities. And now you can make all these extremely precise with, some people say painful, some people say fun technicalities. So this is the world of Fukaya categories or microlocal shift theory. So there is a way to build a category, an infinity category in the floor theory case, such that the objects are the Lagrangians and the morphisms between two Lagrangians exactly are the intersection points with one way in which they talk to each other. And that is non-trivial because of this sort of idea that the Morse inequalities generalized persist beyond the graphical case to a general non-graphical case, even with topology given by a Lagrangian. If you're interested after the talk, I can tell you a bit more. The idea of floor theory is to think about holomorphic disks that account for the intersection points. The idea of shift theory, when you apply it, is thinking of the intersection as just multiplying two characteristic functions. So different ways to think about intersections. Each of them leads to a different category. And then down the road, you prove that this information is equivalent. There's some equivalence down the way. And so you can kind of choose your favorite tool to work with. OK? So this is where we are. I just wanted to give you the main highlights. The boundary sees the interior a little bit, and Lagrangians tend to intersect with each other. And now, once you have these flavors understood, understanding that it's a global problem, now you want to solve it. You want to classify it. So here comes the theorem. We're going to read the theorem several times together. So first of all, let's just read the title of the theorem. It says Lagrangian fillings, which is Lagrangian surfaces with a specific boundary condition. We say fillings because we think of it as like filling the boundary condition. So that's the part we've been talking about. And then on the right-hand side, it says cluster algebras. Whatever this is, it's to do with algebras. Okay? It's not to do with geometry. You can learn cluster algebras without ever drawing a picture. Not that you should, but you can do that. And now the idea is that there is a way to bridge between this world of Lagrangian surfaces and the world of cluster algebras in a way that you can get a cluster algebra out of these Lagrangian fillings and conversely use the cluster algebra technology to learn about Lagrangian fillings. I'll spoil it for you already. The conjecture is this is a perfect bijection. And what the theorem says is the bijection can be set up and it is surjective. And so the conjecture that's left is it is injective. Okay? But I'm going to read it with you all together. So the first thing you try to do in this case is you fix the boundary condition and you try to think, and you're working with different people, maybe you hear some talks, and you hear the word moduli sometimes in algebraic geometry, a moduli of something. You say, oh, maybe I can build a moduli, quote unquote, of Lagrangian fillings. First challenging aspect about that is Lagrangians themselves are an infinite dimensional space. And the symmetries that you have to quotient by, the gauge group, is also infinite dimensional. These are Hamiltonian things. So now you're already in a kind of tricky business, because it's not exactly algebraic geometry. It's not exactly Riemannian geometry. We say the Lie group of symmetries, the isometries, tends to be finite or compact. Now you have an infinite divided by infinity. But the good news is infinity divided by infinity in this case, it's a finite number. So maybe it's not too bad. And the first thing that the theorem says is you can come out with a way of specifying that moduli. There is a space that will act as our putative moduli of Lagrangian fillings. It's not officially a moduli yet, but there is a space M lambda, that's the one I draw there in red, that has the following properties. Number one, a Lagrangian filling gives you an open toric chart. So in here, I draw for you M lambda. And for a moduli, you would say a Lagrangian filling gives you a point. Well, really, this is parameterizing Lagrangian surfaces plus local systems in them, like GL1C local systems. So if you just let the local system vary, then you get that one Lagrangian filling of the boundary condition gives you a toric chart like this one, C star to the D, an open set inside of your space. Okay? So in that sense, the filling gives you this toric chart, and another filling maybe gives you another toric chart, so on and so forth. So that's the first thing you learn, that given a Lagrangian filling, at least you can name an open toric chart inside of this space. Statement number two is a statement about the geometry of this space. The precise statement is the coordinate ring of functions is a cluster algebra. What does it mean geometrically? It means two things. It means that up to codimension 2, your space is covered. It has an atlas by open toric charts, like this one. And second thing, the transition functions are given by some very specific formula. How does that formula come to be? Well, the specific formula comes from the fact that for every toric chart, being a cluster algebra is also asking that you have a coordinate system. So part 2 is about a Lagrangian filling will not only give you a toric chart, it will give you a toric chart with a coordinate system in it, in a way that you can cover the manifold with toric charts like this one, and such that the transition functions are very specific. I keep saying very specific and not telling you what the formula looks like. The formula looks like a reflection along an axis, or a hyperplane, orthogonal to an axis. The complete statement, which is cluster A mutation, it's essentially the dual of a reflection along a hyperplane. But it's a very rigid transition function. And being a cluster algebra is telling you there exists this atlas of toric charts, each of them with a coordinate, and such that the transition function is exactly the reflection along one of the hyperplanes. So if you attended Professor Geis's talk yesterday, that has to do with his cluster structures. But at least geometrically, this is one way I want to present it to you. OK, so what have we set up? Well, now 1 and 2 set up the space and the fact that this space has very particular geometry. If you like toric varieties is the case of a cluster variety with one torus. This is like many, many tori that all kind of glued together in an interesting combinatorial way. So part 3 is I could start with my space. Maybe I have one filling. It gives me one chart. But maybe the algebra, and these are the gods of algebra, not me doing geometry, tells me, well, because it's a cluster algebra, there's all these tori that cover my space. So I'm going to pick this one. Where is my filling? Did it come from a filling? Because the algebra tells me this atlas exists. Typically, infinitely many tori are needed. And all I know is that I have one maybe given by that. How do I know that that one far away is also given by that? And the part 3 of the theorem is every such torus comes from a Lagrangian filling. So it's a statement about search activity of the map from Lagrangian fillings to cluster seeds to these kind of seeds inside of my space. And now the conjecture is this is actually injective. So in fact, what I conjecture is if you have two Lagrangians, L and L prime, and you get the same toric chart inside of the modelized space, then necessarily they have to be exact Lagrangian isotopic, Hamiltonian isotopic. And should that be true, what this does is it takes the problem of classifying Lagrangian surfaces in symplectic four manifolds, in this case locally in R4, into a reasonably tractable algebraic problem. It's still a beautiful problem, it still has its challenges, but it makes it really algebraic. And so should this bridge be complete, and we know it's true in 1996, it was proven for the unknot. A PhD student of mine proved it 2 months ago for the Hopf link. We're very slowly getting there. But we know it's true in some cases. There's evidence for it. Once if we ever do the injectivity part, that's going to be a complete classification purely in terms of algebra. All right? Let me do a couple of comments on a precise example. So let's take the 4-ball, and let's take the trefoil at the boundary. I'll draw it like that to indicate it's the max TBE trefoil. And now you ask for Lagrangian fillings with boundary that trefoil, and they have to be genus 1. And you ask, how many do I have? Do I have 1, 3, infinitely many? I don't know. So what you do is you build that modelized space, and you compute it. And in that case, I did that for you. You get exactly this stack. It's really an algebraic variety. So in this case, it's a kind of a nice stack. So you get this algebraic variety. And when you go to the Fomin-Zalevinsky papers on cluster algebras, this is a pretty well-known example. And its coordinate ring has A2 type, corresponds to the intersection of that gamma 1 and that gamma 2 curves in there. So in particular, you know exactly that it should have 5 cluster seeds. The thing is covered by 5 cluster tori. So that's one way to guess, OK, I'm going to have 5 Lagrangian fillings for the trefoil. That's one thing the theorem is doing for you. It's giving very good guesses about how much you should expect. In this case, we know there's at least 5. Conjecture is there's exactly 5. And that space is another description for people who like more intrinsic ways of thinking about things. Instead of these coordinates, this space, what it's doing, it's parameterizing tuples of lines, L1, 2, 3, 4, 5, which are consecutively distinct modulo reparameterization. And the reason I'm giving you this description is to give you the flavor that, in general, the kind of modelized spaces, these are algebraic stacks. They're really nice, locally finite presentation. They're smooth stacks. They're kind of nice spaces. These guys are parameterizing some moduli in algebraic geometry, specifically in incidence problem of flux. The general description of this m lambda is you have a tuple of flags, and then a flag has to be in a certain transverse position with respect to the next one. So maybe I have a point, a line, a plane in R3, and then the next one has to be the same point, the same line, not the same plane. I have to change the plane in the next one. And you have like configurations of flags with these transversality properties, very much generalizing the classical sort of Schubert theory, intersections of cells, to do enumerative geometry. So those are nice spaces that generalize nice algebraic varieties that we understand to a larger class. And in general, they appear naturally from symplectic topology when you're trying to parameterize Lagrangian fillings. OK, my last comment on this is something I kind of mentioned already. It's just, by the cluster theory, you know you're going to have 5. So the theorem tells you there's at least 5. I conjecture there's exactly 5. And just to show you that this can be done very precisely, I wrote for you the exact equations for the tori. So this is saying the first tori is given by the non-vanishing of z1 and the non-vanishing of 1 plus z1, z2, and giving the coordinate rings of functions. So that's precise. I would be lying to tell you that if you take a very wild lambda, this is as nice. But the good news is that people have developed software for that. So now you can go and compute stuff, and you don't have to do that. So it takes a while to set up the whole thing, but once it's set up, it's kind of black boxable. You can just say, OK, this is a 100-page paper. No, you just use that, put it in the software computer, and then you play with the computer, and that's kind of nice. So again, one take-home version of the theorem is you have built a space M lambda that acts as the putative, as the potential moduli space of Lagrangian surfaces with that specific boundary lambda. And the geometry of that space is really combinatorial in nature. It's not quite a toric variety, but it's built out of combinatorial tools and clustered tori, these different toric charts, and that makes it rather accessible. Now, part 3 of the theorem says it is surjective, meaning every such torus in my variety comes from a Lagrangian filling, and the conjecture just says that is injective. If I had 2 fillings with the same torus chart, conjecture is maybe they're the same, and then you're done with the classification. OK, quick comments. So first one, being a cluster algebra, as I said, is in spirit similar to being toric. There's a lot of beautiful software out there. There's software in Sage Math, which is an open source. And then in Sergei Fomin's cluster algebra portal, there's a software section. And there's tons of apps related to quiver mutation, related to representations, so on and so forth, Plavik graph, so on. So that makes it rather tractable in the sense that if you initially were just thinking about surfaces in 4D, it might seem hard to draw. And this becomes a rather algebraic combinatorial problem. OK, so you prove the theorem. I think I summed up. It's 490 pages. But so now you move on. You're like, OK, this is done. So what I did is a summary of the different results from different papers. But you're done, and you're like, OK, take a week of vacation, come back to work. What is this theorem useful for? How can I actually prove things that were not known before that use that theorem? So the first thing is that Sergei Fomin and Zalavinsky, after introducing cluster algebras in 2000, have had a really rich school of results building on work of a lot of people, including themselves. So you have 25 years of cluster theory that you can export to symplectic topology. For instance, one of my favorite results of Fomin and Zalavinsky is that there exists an ADE classification of cluster algebras. So whatever this cluster algebra is, they come in 3 types: finite, tame, and kind of infinite or wild. So remember that there's always this trichotomy, like positive curvature, 0 curvature, negative curvature, like positive Kodaira dimension, 0 Kodaira dimension, general type. It's always like platonic solids, tilings of the plane, and then hyperbolic business. So there is such a thing for cluster algebra. There's an ADE family where you have finitely many toric charts. Then there's the tame ones, which is like infinite, but up to symmetries it's finite. And then you have the wild world of cluster algebras. In particular, you learn that a typical cluster algebra has infinitely many toric charts. Because the ADE classification tells you if I draw a random quiver, I'm going to have an infinite family of toric charts. So now you learn that given any boundary condition lambda, actually what you ought to expect are infinitely many fillings. Now, I proved that result first, maybe in 2022 or 23, and I proved it in a kind of very ad hoc different way. By then, so 3 years ago, we didn't know one example of infinitely many Lagrangians within the same smooth class. It just wasn't known. We were all expecting maybe finitely many numbers, and then I sort of started to build these infinitely many examples, but I didn't have a conceptual reason for that. So now we know that, in fact, it's not just my weird examples existed. Now with my second theorem, now you know actually this is the generic behavior that you should expect. Also, in the case that you have finitely many, you know exactly what numbers to expect. For the trefoil, you would expect 5. For a 2n torus knot, you would expect a Catalan number, so on and so forth. Also, having cluster algebras allows you to compute cohomology, even the Hodge numbers, like refine decompositions of cohomology in a very nice way. So that's rather useful stuff. And then the second thing is to go the other way around. So this is use cluster algebras to prove results in symplectic topology and get a better sense conceptually. But now you want to give back. You say, OK, I have all this symplectic business, and the cluster algebra people are telling me about some questions they don't know about. And in particular, somebody told me that open Richardson varieties, I think it was Jose Cimental, he told me open Richardson varieties were not known to be clustered. It was not known that the coordinate ring of a Richardson variety, say from a general Lie type, was a cluster algebra. And this is something that Bernard Leclerc and other people had worked on a lot. And what do you do? So, well, I have a theorem that says these people are cluster. And I have a question, which is this guy cluster? Well, if Richardson varieties appeared as the model A of Lagrangians, then my theorem would tell you they're a cluster. And that's exactly the proof. The proof is, given the data, the algebraic data for a Richardson variety, 2 permutations UV in the Weil group, then I built for you a boundary condition, lambda UV, such that the model I of fillings for that boundary condition is exactly the open Richardson variety that you wanted. Therefore, by the theorem, that ring is a cluster algebra, so you solve that problem. It also works for any type, any Lie type, not just GL or SL, not just type A. It works for G2. I don't know, it's fun to think about Richardson varieties in G2, and we have a theory, and it works, and they're clustered. So that's one way to give back to the cluster community by saying, here's another way to think about these varieties as moduli of fillings, and by its nature, it's then going to be clustered. OK, so my last few comments are some key ideas in the proof. So key ideas in the proof is to tell you how this M lambda is built, and then how do you prove 2 and 3 too. So for number 1, M lambda is defined as the moduli space of objects of a certain category. So the way it works logically is you first name a category. In this case, it's the category of the DG category of sheaf with the sheaves in R2 with singular support in a given lambda with some compact condition, categorically compact objects. And then you start to study that category. That category is nice enough, it's called finite type, such that you can extract a moduli of pseudo-perfect objects. So this is work of Toen and Vacquier in their work in homotopical algebra geometry. So what this space M lambda is, it's a D minus stack, but you can just think of some relatively nice space that's parameterizing objects, certain kinds of objects with certain finite conditions in them, inside of this category. So out of lambda, you name this category. If you prefer Fukaya categories, you name a Fukaya category. And out of that, you get this space. Note that there's no stability conditions. There's no GIT. This is just raw. You just take the moduli of objects, and you can make sense of that. OK, so that's how you build M lambda. The fact that you can go from L to TL, it's a form of Schiff quantization. So these type of results were actually sort of in the literature in some form or another, the Schiff quantization part. Not exactly this one, but it fits within a line of results, which again, it's saying it's about an operator looking like a Fourier transport. Essentially, the problem boils down to you have some functor that you know nothing about, and you want to show that it comes from pullback, tensor with something, push forward. Again, you have a function f of x. You want it to look like f of x times kernel of xy, and then you integrate out the x to get a function of y. So that kind of transform, Mukai-type functors, when you apply it to this technology, you prove that the necessary functors are of this type, and then you get this kind of Schiff quantization result. OK, so how do you prove this cluster algebra business? Now, the cluster structure is built on actually not just building the fillings, but the idea, I would say, the idea that sort of for me made everything click and move forward quickly was that I should not just be looking at Lagrangian fillings L, but I should be looking at what I call relative Lagrangian skeleta, which are Lagrangian fillings plus Lagrangian disks on the complement such that the 4-ball retracts to that. So in a way, you have now this Lagrangian filling, this surface, and you add Lagrangian pieces to it in a way that the whole ball retracts to it through the Liouville flow. And how do you build this? That's kind of a hard technical part, and this is these whiff techniques. But once you develop these whiff techniques, which is, again, it's kind of black boxable diagrammatic calculus, you get not just the Lagrangian surface, but the Lagrangian surface with these disks attached to it. And now once you have those disks, you can do the following operation, known as Lagrangian disk surgery, which is you take one of these disks, you contract it down to a point, and you expand it in a slightly different way. This very much looks like xy equals 0, and you could go to xy equals 1 and xy equals -1, like the two hyperbolas, this one or this one. It's exactly that, but now in 2D, we have a version of that. And what you do is you take one toric chart, say this one, it comes from the filling, and the way you transition to the next toric chart is you squeeze a point and you go up. My point being, the fact that this is a kind of universal geometric transition is what makes the transition functions in the atlas be so universal. It's because it comes from a geometric construction that actually this guy has only two resolutions, this guy or that guy. So that's exactly, it's universal in this sense. It's a unique way to resolve these two guys. And that's how you prove the cluster algebra part, again, intuitively. And the last thing that I won't have time to say is, to prove surjectivity, you reduce first the problem of Lagrangian surfaces in 4D to a problem of curves. You maybe see here the curves in a surface. And you forget about the surface being Lagrangian. Now it's literally a smooth surface with some curves in it. And now you try to understand how those curves behave as you go through this process. And they behave in a really beautiful but also weird way. People that intersect positively are acted by a dent twist, and people that intersect negatively are left as is. So as you go through that, some people get a dent twist, like this guy gets dent twisted, and the others don't at all. And you want to understand now the combinatorics of curves and surfaces as you act by this operation of do dent twist to some of them but not the others, and iterate that. So I thought about it for a while. I was lucky enough to be visiting Michigan at some point, and I talked to Alex, and he pointed me to the Scott Haas algorithm, and from there it really like unraveled a lot, so thanks officially. And out of that, what I built was a quiver with potential. That's sort of the hard part of the technology, and showed that the surjectivity would follow if I knew that the Jacobian algebra has a trivial deformation space. So that's what we call a rigid potential, which implies non-degenerate. So that suddenly became a problem in representation theory. And you solve the problem in rep theory, then you solve the problem about curves and surfaces, and then you solve the problem about Lagrangians. So it was sort of a sequence of events about sort of different pieces of math fitting together. And I wish I had a bit more time, but you're absolutely welcome to ask me afterwards. Now, to end, I want to reiterate my thanks to the MCA and just show you some faces of some of my nice colleagues and people who have helped me along the years. So Victor Ginsburg, he was not my official mentor, but he really helped me a lot during grad school. And I'm currently collaborating with Jose Cimental and Melissa Sherman-Bennett in trying to understand cluster algebras from this perspective of weaves and so on and so forth. And just point out that there's a number of sections in this MCA that do connect to mathematics that are behind here. And I think I will leave it at that. Thanks a lot for listening.
Are there any questions?
Yes?
Why restrict to exact Lagrangians?
Right. So if they're non-exact, first of all, you can actually have closed things. And so there's interesting tori in R4, like Clifford and Chekanov and so on. So that's the first thing that the problem becomes very, very different. Now, one way to think about it is that the non-exact case comes as a deformation of the exact case, in the sense that what's happening is you have an exact Lagrangian, and your torus really has period 0 as I integrate. When you consider local systems, so I said the model I really is about Lagrangians and local systems. So the local system, you can think of it as providing a non-exact deformation. So the exact Lagrangian sort of is this special point in the model I that you can really work explicitly with, and you can actually draw with pictures in 3D via caustics. But if you want to deal with the non-exact case, what you do is you take that guy and you introduce local systems that are deforming in those classes. So in a way, what this is doing is also dealing to some extent with non-exact deformations, in that you first deal with the exact case and then you deform. And that would allow you to understand non-exact Lagrangians with a given asymptotics. Now, if you ask, OK, what about I have no asymptotics whatsoever, but I just want to understand those tori locally, I would say that there is a part of symplectic geometry that's sort of dedicated to that. And the methods of shift theory and the floor theory that kind of works, for exact Lagrangians, you need to extend that technology to non-exact ones. So when you deal with non-exact, you need Novikov coefficients. You need to start being able to keep track of holomorphic disks bounding by these things, and the area of the holomorphic disk, that gets tracked. So I would say the technology has been evolving, but the technology, the part of have a floor theory, have floor groups, have a category, it's really not completely there yet in the non-exact case. I think once it would be there, one would be able to try to develop a general theory. There are examples. I think non-exact Lagrangians in like T star S3 and some other examples are starting to be understood. But I would say the thing that you can try to do with the current technology is really the exact case. Deform a little bit to get some non-exactness. But if you want a global theory of non-exactness, then you need to go to the world of Novikov coefficients, rigid rings, so on and so forth. Which I hope maybe in 5, 10 years I can tell you, oh, the same story works, it's just with these weird coefficients. But we're not there yet.
Any other questions? Sorry, yes.
How does stabilizations of the Legendrian boundaries affect the filling?
It kills it.
Completely kills it.
Completely kills it.
Only when you're non-destabilizable.
If you're not max TB, there's no filling.
There is no filling.
Yeah.
Is that the only case there's no filling?
My conjecture is yes. I mean, my view on this is everything the algebra tells you, everything the DGA would tell you, the Legendrian contact DGA or the shift theory or the contact homology, everything should be geometrizable. So every time you have an augmentation or you have a ruling, my view is there ought to be a Lagrangian filling. The problem is that we've been sort of been narrow-minded in that we've insisted on wanting embedded Lagrangian fillings. And there's a story, which I have not yet developed, but there's a story of immersed fillings, which are unobstructed. My view is every augmentation comes from an unobstructed Lagrangian filling. And in some cases, Pan Rutherford and company have established that. So my view would be, yes, if the algebra tells you there's something non-zero, it means geometrically there's something non-zero. It might not be embedded, so it's not exactly this technology, but it might be immersed and obstructed, and then you're good to go. Does that make sense? Yeah. But if the DGA is 0, it says no fillings, which you already kind of knew for other reasons.
And then you can distinguish different max TB Legendrian realizations of non-types.
Yeah. I mean, in fact, it's kind of, say you take the Legendrian DGA for a second, you take the augmentation variety, that might actually have different components. My conjecture is that the different components exactly give you different smooth types of the Lagrangian fillings. So it could be that within the same lambda, you would have two different, I think the mirror of 946 is a Lagrangian slice, which is two different disks. Both of them are not smoothly isotopic. But when you look at the variety, it's two different components. That also happens with the mirror of 821. It's a 282, it's like that. So the number of components of this M lambda, actually, I suspect it's exactly telling you about the smooth information of those Lagrangian fillings. But that's not proven, so I cannot put it on a slide. But, yeah.
Any other questions? If not, thank you again.